Hello and welcome to the course Design Bore Fields with Confidence. This is the second chapter of the fourth part, and we will be continuing our discussion about the hydraulic design of bore fields and the pressure drop in general. Now, last chapter we introduced the pressure drop, and we said that the pressure drop has both a local component, and the sum of all the local losses, the bends, the junctions, etc. And we have the friction losses, which are more spread out, also called the major losses. And this is given by a certain friction factor, which depends on the Reynolds number in the Moody diagram and so forth, multiplied by the length of the pipe divided by the pipe diameter. And the sum of both actually was multiplied by the rho, the velocity, squared divided by 2 to get the overall pressure drop over your hydraulic circuit. And this gave us, as is visible in the slide, this typical quadratic behavior in the flow rate. Now here we ended last time. But of course, as we discussed in the last part, part 3.2, we said, well, actually the fluid properties, the density, viscosity, the Reynolds number as well, is not constant over time, because the temperatures in a bore field, they fluctuate, and hence do the fluid properties. And this means that our density in this equation, as well as the friction factor, which depends on the Reynolds number, they are not constant, they fluctuate. So we do not have one pressure drop, but we actually have a couple of them. And that's why when you're designing, as you will see in the next chapter, the hydraulic design in GHE tool, you actually will be working with two different lines. And one is the pressure drop in function of the flow rate at the minimum average fluid temperature threshold during extraction. And the dotted line is the same line, but now during injection, when the fluid temperatures are high. And what you can clearly see here, that these jumps, where we transition from laminar to turbulent flow, they occur at different moments. We need, when we have this higher temperature, this lower viscosity, we are transitioning from laminar to turbulent flow around 0.5 liters per second, whereas our fluid is colder during extraction. It takes a higher flow rate, a higher Reynolds number to transition towards this turbulent transient flow regime, around somewhat higher than 1 liter per second. And when we're now talking about the pressure drop, and you say, well, what's actually the critical pressure drop? It depends on your system, because sometimes, your extraction is more or less dominant. For example, in the lower flow rates, in this case, imagine you have 0.4 liters per second. You will be looking at the pressure drop during extraction for your pump design, your pump selection. But on the other hand, if you have higher flow rates in the neighborhood of 0.8, 0.9, it will be actually the injection, the cooling, that will be the most prominent, the most dominant, and the deciding factor for your pressure drop. So given these graphs, it's easy for you as a designer to see, okay, what do I care about the most? What's the most critical when we're designing? Is it the injection or the extraction pressure drop? But this, of course, it's a graph. There is no time in it, let's say. It's depending on flow rate. But what we can also do is we can plot an hourly pressure drop curve of the system. And that you see here. So this is a close-up of the pressure drop at every hour. Through specific bore field details are, again, over in the textbook. And what you see here is that it's a very ugly graph, basically. There are quite a lot of jumps, especially in winter. But in summer, you see a smooth line. It's not smooth, it's still jumpy, but at least there is some continuity, let's say. And this is because in this case, as we discussed again previously, we are warm, it's summer, we're cooling with our bore field, we're injecting heat into the ground. So we're almost always turbulent in this case. This gives us this smooth behavior. Whereas in winter, you can see the temperature fluctuates quite a lot. It's also the first year. So this means that we're transitioning from laminar to turbulent back and forth, giving us these big jumps from 18 to 30 kPa. And to prove that, or to illustrate that, we can compare this pressure drop graph with the temperature plot. So this is again a zoom in on the first year of the fluid temperatures in the borehole. And you can clearly see that at the end of January here, where we have a very long period, a rather long period with low temperatures between 2 and 4 degrees Celsius, we see that we also have a long period for the pressure drop where we will be in this lower pressure drop range, where we will be laminar. And you have the same somewhere in March. There is again a spike down in temperature, where again there is a spike down in the pressure drop as well. So this indicates the relationship between the pressure drop and the temperature due to the fact that we are transitioning from laminar to turbulent flow back and forth. And to illustrate that somewhat further, what we also did is we simulated the same system now with twice the flow rate. And here you can see that we do not only have this continuous behavior in summer, but also in winter, meaning that the transition from laminar to turbulent is totally gone, and we have now this smooth line, which, as sure you noticed, we're now not at the maximum of 30 kPa, but higher, because our flow rate has been increased, so our overall pressure drop is also higher, of course. Now this is what I wanted to say about variable fluid properties and its relationship to the pressure drop. But what is interesting is that the graph you see here, as well as the graph previously here with all the jumps, these were all with a constant flow rate. So the flow velocity to our bore field was constant in peak and off-peak moment and during heating and cooling. But as discussed in part 3.3, this is not the case. Typically, pumps are now frequency controlled and the flow rate varies from hour to hour. So this also has, of course, quite a lot of impact on the pressure drop and the Reynolds number and so forth. And this is a graph we get when we're working actually now with the variable flow rates. And instead of being between 80 and 30 kPa, here we see that just by looking, let's say 50% is below the 5 kilopascals. And that's because most of the year we do not work at this maximum peak power. We're actually way lower, meaning that on average our flow rate is also way lower. And this is clearly visible if we compare it to the actual building demands. You see that the peaks where the power is the highest, both in summer and in winter, when the peaks are high, also the pressure drop is high. Because having a high power means that we will have a higher flow rate, and this higher flow rate has also a higher pressure drop. And that's why you can see more or less the same curve, the same shape, let's say, for the energy profile in the pressure drop curve. Now, what is also interesting is that when we're heating and cooling, and you see here in heating we go up to 15 kilowatts, in cooling we're only at 10. But if we look at the pressure drop during cooling, in summer, we reach 20 kPa, where in winter we reach 22 or 23 kPa. So the difference in peak power, 15 to 10, is actually, compared to cooling, 50% higher. But if we compare the pressure drops, yeah, it's not like the one is at 30 and the other one is at 20. No, it's 20 and just slightly higher. And this also illustrates what we discussed in the last slide, these variable fluid properties. In winter, the fluid is also warmer. So what determines the turbulence is not only the flow rate itself and the amount of liters per second or cubic meters per hour, but it's also the temperature, the viscosity and so forth. So that's why in this case, although the required power in heating and cooling is different, significantly different, when we take a look at the pressure drop curve, it's more or less similar because of fluid temperatures and the change of the hydraulic behavior of the fluid counteracts are placed together with the higher flow rates. Now, let us go one step further, because pressure drop is all interesting, but actually we need to design a pump, and this pump has to have a required power, a certain amount of power. And the way we define this power is we have a certain hydraulic power, which is actually the amount of effort we need now expressed in kilowatts or watts to pump the fluid through the system. And that's defined as flow rate of the system multiplied by the pressure drop across it. And that gives us the hydraulic power. Now what is important is that this hydraulic power, it's not the electrical current you will draw. Because the hydraulic and the electrical power are not the same. Because, well, a pump, it has an electric motor that has a certain electrical efficiency, typically rather high, 95, 98%. But then we have also the hydraulic efficiency. Because we have a certain impeller in this pump, it turns around, but not all the electrical, at that moment the mechanical energy on the shaft, gets translated to hydraulic power. So also there is some trade-off, some losses in efficiency. And if you take a look at a graph on how the pump efficiency behaves, both electrical and mechanical, you see that typically it tops off at 80%, some pumps have 70, other pumps have 90. There's quite a lot of difference there. But typically it tops off there. And when the flow rate increases even further, the efficiency goes down a little bit. And when we go lower and lower in flow rate, also the electrical or the overall electric efficiency of the pump to convert hydraulic power to electrical power goes down. And typically, at least that's the advice of Grundfos, is to stay within this bold region, in this case from 75 to 200 cubic meters per hour for this pump. So it's a rather big system. Now, that's really important if you as a designer are selecting a pump. Because if you're working with variable flow rates, you can say, well, I want my maximum power to be exactly at this 150 cubic meters per hour here, right at the highest efficiency. But then you know that most of the year, you will actually be working at a lower efficiency. Whereas if you say, okay, let's design our pump with the maximum flow rate at right the end of this graph, not the highest efficiency, but then you know that when you're playing around with your flow rate, it varies over time, that you will actually, when you go into part load regime, that your pump will have a higher efficiency. Which is interesting because, most of the time, most hours, you will be working in this region of a higher efficiency. And that's interesting to consider when we're talking about pump power. And if we then talk about electrical power, it's the same equation, but now we divide it by the efficiency of our pump, which is typically, let's say, 70%. Now, the pump power itself, it's an interesting quantity to reason about, but what we're actually interested in is the pump energy demand, the pump electricity consumption. Now, here we need to make a distinction between hourly and monthly simulations, because when we do an hourly simulation, calculating the pump energy is actually quite easy, because, well, we know the flow rate at every hour, we know the pressure drop at every hour, as we discussed, and then we can calculate the power at every hour. And when we know the power at every hour, we can simply sum it and have the total energy demand for the pump for every year of the simulation period. And this, you can see here on this graph, it's the cumulative pump electricity consumption. And what is really clear is that when you have a variable flow rate, it increases, but it's way, way lower than when we have a constant flow rate. And if we compare it, actually on a yearly basis, a variable flow rate consumes 92% less pump energy, requires less electricity to run, than the case with a constant flow rate. At least in this simulation. Of course, it will depend on your specific situation. So the savings you can make in the electricity consumption are actually quite big. Now, this is for the pump electricity consumption. But what is interesting is we compare it to the overall energy consumption of the system, taking also into account the way the heat pumps work and the electricity consumption of the heat pump. It's lower. It's just 4.5%. Because of course the electricity consumption of the compressor is an order of magnitude bigger. But still, just switching from constant to variable flow rates will give you an increase in overall system efficiency due to the lower electricity consumption. So this was the case for an hourly simulation. When we do it monthly, it's a little bit difficult because here we need to make assumptions because we do not know the pressure drop at every hour. And we make a distinction between working with a constant flow, a monthly simulation, and a variable flow, a monthly simulation. So what we can do when we have a constant flow, we calculate the maximum pump power. It's not difficult. We have the maximum minimum temperatures. We have the flow rate. So we calculate the most critical pressure drop, being in extraction or injection. And what we do is we take this maximum pump power and we multiply it with a number of full load hours. So we estimate how long this pump will work at this maximum pump power. And the way we do that is we take the base load, extraction, injection every month, and we divide it by the required power in every month, and that we sum. So we have a rough estimate of how many full load hours this pump will have. We multiply this by the pump power and we end up with a certain energy, pump energy. When we do it with a variable flow, the reasoning is a little bit different, because here we're going to calculate the maximum pump power, for every month. Because the temperature fluctuates every month, so we're going to calculate the maximum power at every month. And then we multiply each month with the full load hours in that month. So instead of working with one maximum power for the whole simulation, multiplying it with the sum of all the full load hours, we do that now month per month. And this gives a little bit a better estimate of, it will give a lower estimate at the electricity consumption of a pump will be lower in this case, of course. But as you can see in the textbook as well, where we've written it out in way more detail, doing this type of simulations with an hourly profile gives you a way better insight in how much the pump electricity will actually be. But at least these monthly assumptions can give you some feeling, let's say a threshold or just an idea of the importance of working with constant versus variable flow. So these were the deepening insights in the pressure drop, pump energy, and pump power that I wanted to give. And in the next chapter, we will make it more practical. We will talk about the hydraulic connection, the hydraulic design of your bore field. We will talk about single versus double U probes, and we will see how you can make these type of designs, calculations inside of GHG2.